In this lesson, we will be learning about 3 symmetric encryption algorithms. Specifically, we will discuss the Advanced Encryption Standard, or AES, Blowfish, and Twofish. The more popular and widely adopted symmetric encryption algorithm likely to be encountered nowadays is the Advanced Encryption Standard, or AES. It is found to be at least 6 times faster than triple DES. Recall that a replacement for DES was needed as its key size was too small. With increasing computing power, it was considered vulnerable against the exhaustive key search attack. Therefore, triple DES was designed to overcome this drawback, but it was found to be slow. So the features of AES are as follows. It has a symmetric key, symmetric block cipher, 128-bit data, 128, 192, or 256-bit keys. It's stronger and faster than triple DES. It provides full specification and design details, and the software is implementable in C and Java. AES is an iterative rather than Feistel cipher. It is based on substitution permutation network. It comprises of a series of linked operations, some of which involve replacing inputs by specific outputs, or substitutions, and others involve shuffling bits around, or permutations. Interestingly, AES performs all its computations on bytes rather than bits. Hence, AES treats the 128 bits of a plaintext block as 16 bytes. These 16 bytes are arranged in 4 columns and 4 rows for processing as a matrix. Unlike DES, the number of rounds in AES is variable and depends on the length of the key. AES uses 10 rounds for 128-bit keys, 12 rounds for 192-bit keys, and 14 rounds for 256-bit keys. Each of these rounds uses a different 128-bit round key, which is calculated from the original AES key. The schematic of AES structure is given in the following illustration. Here we restrict to description of a typical round of AES encryption. Each round comprises of 4 sub-processes. The first round of process is depicted in this illustration. Let's begin by discussing byte substitution, or sub-bytes. The 16 input bytes are substituted by looking up a fixed table, or SBox, given in design. The result is in a matrix of 4 rows and 4 columns. Next, let's discuss shift rows. Each of the 4 rows of the matrix is shifted to the left. Any entries that fall off are reinserted on the right side of the row. A shift is carried out as follows. The first row is not shifted. The second row is shifted 1 byte position to the left. The third row is shifted 2 positions to the left. The fourth row is shifted 3 positions to the left. And the result is a new matrix consisting of the same 16 bytes but shifted with respect to each other. Let's discuss mixed columns. Each column of 4 bytes is now transformed using a special mathematical function. This function takes as input the 4 bytes of one column and outputs 4 completely new bytes, which replace the original column. The result is another new matrix consisting of 16 new bytes. It should be noted that this step is not performed in the last round. Finally, let's discuss add round key. The 16 bytes of the matrix are now considered as 128 bits and are XOR'd to the 128 bits of the round key. If this is the last round, then the output is the ciphertext. Otherwise, the resulting 128 bits are interpreted as 16 bytes and we begin another similar round. The process of decryption of an AES ciphertext is similar to the encryption process in the reverse order. Each round consists of the 4 processes conducted in the reverse order. Add round key, mixed columns, shift rows, byte substitution. Since subprocesses in each round are in reverse manner, unlike for a Feistel cipher, the encryption and decryption algorithms needs to be separately implemented, although they are very closely related. In present-day cryptography, AES is widely adopted and supported in both hardware and software. To date, no practical cryptanalytic attacks against AES has been discovered. Additionally, AES has built-in flexibility of key length, which allows a degree of future-proofing against progress in the ability to perform exhaustive key searches. However, just as for DES, The AES security is assured only if it is correctly implemented and good key management is employed. In this lesson, we will be discussing Blowfish. Blowfish is a keyed symmetric cryptographic block cipher designed by Bruce Schneier in 1993 and placed in the public domain. Blowfish is included in a large number of cipher suites and encryption products. Blowfish's security has been extensively tested and proven. As a public domain cipher, Blowfish has been subject to a significant amount of cryptanalysis, and full Blowfish encryption has never been broken. Blowfish is also one of the fastest block ciphers in public use. Schneier has designed Blowfish as a general-purpose algorithm intended as a replacement for the aging DES and free of the problems associated with the other algorithms. Notable features of design include key-dependent S-boxes and a highly complex key schedule. Let's take a closer look at how Blowfish works exactly. Blowfish has a 64-bit block size and a key length of anywhere from 32 bits to 448 bits. It is a 16-round Feistel cipher and uses large key-dependent S-boxes. It is similar to structure to CAST128, which uses fixed S-boxes. This diagram shows the Blowfish's F function. The function splits the 32-bit input into 4 8-bit quarters and uses the quarters as input to the S-boxes. The outputs are added modulo 232 and XOR'd to produce the final 32-bit output. Let's quickly summarize Blowfish. Blowfish is a public domain algorithm which was designed originally as a DES replacement. It uses a Feistel network and combines substitution and transposition. Blowfish is one of the fastest block ciphers in widespread use, except when changing keys. Each new key requires pre-processing equivalent to encrypting about 4 kilobytes of text, which is very slow compared to other block ciphers. This prevents its use in certain applications, but is not a problem in others. Blowfish is not subject to any patents and is therefore freely available for anyone to use. This has contributed to its popularity in cryptographic software. Another symmetric algorithm is Twofish. Twofish was derived from Blowfish by Bruce Schneier in 1998. It is freely available in the public domain as it has not been patented. It is a symmetric key block cipher having key sizes of 128, 192, and 256 bits, used to encrypt the 128-bit block size data in 16 rounds. The algorithm making use of S-boxes and makes the key generation process very complex and secure. So in summary, Twofish was designed as a DES replacement. It was placed into the public domain, uses a Feistel network. It combines substitution and transposition. And some of the key facts is that it's symmetric, it's block cipher, and a key length of 128, 192, and 256 bits is what you'll need to remember. Here we have a summary of the algorithms we've discussed. I would strongly encourage you to pause the video now and review the method and key size of each as a quick refresher. We've covered a lot of information, and this summarizes most of that.